Hello, this is Tom from anti-proton.com. Our world is radioactive. Not everything is radioactive, but radioactive things are mixed with nearly everything. For example, your rainwater. Right after it falls, for the first couple of hours, 4 or 5 hours, it can be very radioactive when measured with a Geiger counter. Wonder why? Your kitty litter. Not always radioactive, but sometimes radioactive. Why is that? Granite countertops? God, they look so nice, but sometimes they're very radioactive. Not too much anymore, the industry's gotten better about it, but still. Why? There is actually a method to figure out why things are radioactive. Not just that they are, but what's in them that makes them radioactive. This is called spectroscopy. There are so many different types of spectroscopy that exist in science, things you can't even imagine, all sorts of spectroscopies. But when it comes to radiation, probably the 3 most common ones you'll bump into, well, the 4 most common ones you'll bump into are gamma spectroscopy, X-ray spectroscopy, alpha spectroscopy, and beta spectroscopy. Each one of these works exactly the same basic way. They sense the energy coming from something, and then they display it in a nice little happy graph that you can look at. And from the various little features of the graph, you can kind of pick out and figure out what's in something, like a fingerprint. This is a piece of material from geoelectronics. This little plastic scintillation, it's a bicron scintillation plastic, has an interesting property. When it's exposed to radiation, it causes little flashes of light, little pulses of light, tiny little ones. They can be detected and they can be measured. And the intensity of these, the number of little photons that are emitted, is proportionate to the amount of energy that hit the plastic in the first place. So if a gamma ray hits this piece of plastic, and it's very, very low energy, you get a few photons. If a really, really high-powered gamma ray hits this piece of plastic, it could produce a large number of photons. And because of these difference in counts, you can easily determine how much energy hit this thing in the first place. This is an ultraviolet light. It really has nothing to do with gamma rays or radiation, but just for giggles, it's kind of neat to see that the scintillation material glows, doesn't it? Nice stuff, isn't it? That actually has nothing to do with the fact that it senses radiation, but it looks neat, so I figured I'd show it to you. But more of how these devices work. Where's my marker? Here it is. Here's an example, just a little thought example. This is not quite how it works, but this will give you an idea. Imagine we had a radioactive object, a rock or something, and you wanted to know why. Well, it's spitting off gamma rays, and these gamma rays are coming out at exactly the same every time, the same exact amount of energies. And that's because each isotope that exists, each little atom that is radioactive that exists, of a particular type, will always emit the exact same energy photons. It may emit 5 or 6 different types, 20 or 30 different types, but each one of them is always the same amount of energy. Take cesium-137. Common, right? You hear about it in the news, cesium-137 detected after Fukushima. Well, cesium-137, actually it's a little more complicated. There's some other parts to it. It's not actually the cesium itself that emits it, it's barium-137. But the cesium-137, when it emits a gamma ray at 661.66 thousand electron volts of energy. That's just a measure of how much energy the photon has in electron volts. It's actually a very small amount. It's a tremendously small number. It's like 1 times 10 to the negative 16 joules or something like that. It's a very, very, very tiny bit of energy. But that's how much it emits. It emits it every single time. Well, every single time it emits a gamma ray, it emits that. It actually only emits a gamma ray 85% of the time, but whatever. Look at this. This is a graph. This represents the number of counts detected by the device. This is the Y. Remember XY graphs from, like, I don't know, middle school or something? Right? Counts. 0 counts, 5, 10, 15, 20. This is energy. It goes from low energy to high energy. When a gamma ray strikes something like this bicron scintillation crystal, or in my case, a sodium iodide thallium dope crystal, or a cesium iodide thallium dope crystal, or any of the other little fun things that exist, you have a device called a multi-channel analyzer. And what it does is it takes those photons. Remember I told you the amount of photons that are emitted is kind of like proportionate to the amount of energy that hit the thing? low energy, low photons, high energy, high number of photons. Well, this thing kind of counts them up and says, okay, look, I got one photon, let's just say, it's hypothetical. I got a gamma ray that only emitted one little tiny burst of light. So I'll make a mark right here. The next gamma ray that comes in emits a large burst of light, let's say 10. It makes a mark right here. So one mark per energy. And if I got another one of the exact same amount, you get another mark. 2, then 3, then maybe one over here. So you're starting to fill these little channels up. So each one of these little numbers from 1 to 16 here is a channel. And it represents a discrete amount of energy, ever so increasing, 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 increasing. My unit doesn't have 16, it has 1,024 of them. I just didn't want to draw 1,024 lines. And my unit starts at 1,000 electron volts and goes to 1 million electron volts, the way I have it calibrated mostly. It can actually be changed, but that's the way it is. And so that 661.66 is somewhere over here when it comes through, the one for cesium-137. And as these little tiny photons appear, they'll be all over the place. And they'll start to stack up as they're counted and counted and counted. And this counting process can take hours and days, depending as they show up. But as it starts to happen, you start to get a pattern. See that pattern? And you might be able to then look up in a table of known values, things that other scientists have spent a long time discovering. And you might find out that a peak of energy here and a peak of energy here is associated with a particular known isotope. That's it. That's the gist of it right there. That's basically all it is. There's tremendously more complexities to it, of course, I mean, obviously. But the basic principle is that simple. Let's take a sample from Portland, Oregon. Let's test it for 6 hours, and then let's see what the result is. And I'll walk you through the whole entire step. I'll even do a time-lapse, well, not time-lapse, a sped up of me analyzing the sample, in which I'll take a long, long period of analyzing and compress it into like 1 minute or something, so you can see really, really fast. Alright, let's go to the laboratory. Alrighty, folks, here we are in the laboratory. This is the sample we're going to test. It's from Portland, Oregon. And if you're the person who sent it to me, it's sample number 1, which you might get a kick out of. Anyhow, I have my computer set up right here. As you can see, I have a little fish tank program running in the background because it amuses me. And underneath this, let me pull the camera off here and bring this down so you can see. Underneath this, I have a Spectrum Techniques Universal Computer Spectrometer UCS30. This is the multi-channel spectrum analyzer. It's that device I told you about that takes the actual signals that come from the detector and figures out how much energy they have and then sticks them in the appropriate little channels so that you and I can understand them. And the actual unit itself that is feeding this with information is over here. I keep it inside this plastic tub right here for A, because it protects it, and B, because the plastic actually reduces beta rays that are coming in here from various random objects. I mean, you know, there's beta radiation in your environment. Now I have a thermometer set up right here telling me current temperature inside of the actual chamber for testing and outside of the chamber for testing. Let me move this off. Let me lift up the plastic. And by the way, when you're building a testing chamber, you have to test everything that's in the chamber, because everything from tape to wires, foil, you name it, if it has anything in it that's radioactive, even the tiniest little microscopic impurity, your detector will detect it. So now what I have inside of this unit, it's not quite the same as the Micron plastic. What I have is called a sodium iodide thallium doped crystal, and it's basically a sodium iodide crystal, which is something somewhat like a salt crystal. It's not actually a salt crystal, but it's like a salt crystal, sort of, except it has thallium inside of it. And an interesting property is that when it's struck by gamma rays or X-rays, one or the other, it will emit a tiny burst of light, like I said before. Inside here, you can actually see the unit itself. The unit is inside of this. Let me pull it out ever so slightly. See? If you pull it out, it's a tubular object. It's inside here, and it runs about to maybe here. So it's that length. This back part is called a photomultiplier tube, and it's taking those flashes of light that are coming from the front in the crystal that's deep inside of here, and it's taking those and it's amplifying them. You see, when the flashes occur in the crystal, they hit something called the photoelectric material, which produces little tiny bursts of electrons proportionate to the amount of light that hits them. That proportionality stays all the way through the whole apparatus to the very end. That's how we're able to sense energies. This device here is actually a vacuum tube called a photomultiplier tube, and it has many stages that each one increase the amount of electrons moving along proportionately. That's the high voltage input, and that's the data coming out of it. Let's slide it back into the unit so it's flush. Now, let's look inside of this and see what we have. When holding lead, always wear a rubber glove. Technically, you probably don't need to, and I get a lot of flack for this, but why not? They cost like 2 cents a piece, and then there's no risk. It's always a good idea when you're working in any kind of laboratory environment, be it a big professional laboratory, or even your own little private laboratory at your house, to just protect yourself. Also, when working with fluids or dusty sorts of things, wear goggles. I'm not going to worry about these now because this is all solid contained stuff I'm using, and even a mask. Again, none of that's needed for what I'm doing right now, but it's important to keep these things if you're working with this sort of stuff. Just safety's sake. It's a good practice. You see that the little speckles in the bottom of this are paint that flecks off of these bars. They're actually made of lead. I'll go through that in a minute. This is an aluminum and lead shield that's in the back end that protects the back here from getting gamma rays going right down that little center channel. The rest of this is all lead all the way through. Let me pull off the bars. As you can see, a bar looks like gold. I have to paint them so that they're less dangerous because just having exposed lead is a problem. I painted them with gold paint because, well, they look cool. What can I say? But I had to test the actual paint before I actually used it, because if I had sprayed the lead with the paint and the paint were radioactive in any microscopic way, it would have been a problem. This is 180 pounds of lead total. As I move the lead bars out of the way, each one of these lead bars is just heavy. Good grief. I expose the central testing chamber. As you can see, it has copper on one side. I'm going to eventually have copper and tin all the way around the inside to shield it from low-level X-rays. And as you can see, I have a thermal sensor. This little thermal sensor connects out to the actual thermometer on the other side and tells me what the temperature inside the crystal is. And the crystal's right behind here too. Now, before we can use this device, we have to calibrate it. To calibrate it, we need a source. Now, here is a standard source. You might be wondering, why is this inside of a bottle cap? I found that a bottle cap that's been thoroughly cleaned and sterilized allows me to hold this significantly more easily than when it's not. Because in the gloves, these little chips can fall. Here, let me get one that isn't inside of a bottle cap. See, they're fine and they're all nice and everything, but I drop them, I fumble them, I do all kinds of funny stuff. And I find in there in the bottle cap, they're so much easier. You can put them on their side and they'll, oh, not now, look at that, I dropped it, isn't that great? When I'm putting them on their side, they'll sit upright without falling over. And they're just so much easier to work with. So I recommend this as a neat little trick. It looks pathetic when you do it. I mean, people are like, oh, you've got it in a bottle cap. Works great though. This is a cesium-137 source I use of 37 kilobecquerels for calibration. And microcuries, that's 1 microcurie. Whenever I'm trying to calibrate something and I need to know the exact amount of gammas that I'm getting, I use these calibrated sources. They have a 95% accuracy for gamma. In this case, I have europium-152, 37 kilobecquerels, and I have cesium-137 at 3.7 kilobecquerels, 1/10. Look at that. Alright. Now, these are very small amounts of radioactivity, of course, but still, they're enough. So let's take this calibration source of cesium-137, and we'll put it right here. I use a piece of plastic here. The plastic and stuff is to block beta. Beta is kind of like a problem. Because beta radiation, what it does is it strikes all the metal here and it produces little X-rays all over the place, which can be quite a trouble. Now, let's calibrate with our unit. We don't even have to worry about putting the shielding back on for calibration. Alright, so here we are, and we're inside of the actual software now, the UCS30's actual software. And if you recall from the board, on this side we have counts, and this time we have a logarithmic scale of 0 to 16, 16 to 256, 256 to 4,000, 4,000 to 64,000, 64,000 to 1 million, 1 million to 16 million, and this is a logarithmic scale. We can switch this by clicking this button right here, to a linear scale, in which case it goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and so on all the way up here. If we do this using the up arrow, which you can't see me push, but I can push it with my finger, I can change the scale from 0 all the way up to 16 million, just like we saw before on the other side. So this is two different ways of looking at the same data. Let's go back to the logarithmic scale. Now you see I have 0 channel to 256 channel, to the 512th channel, to the 768th, and all the way to the 1024th channel. So as you can see, I have 1024 channels, and when I click on one, I'm on channel 164, and use the arrow key to the right, 1, 2, 3, 4, 5 clicks, I'm on the 9th, and then this or 169th, and now I'm on 170th and 171st. So you see that you can scroll through the channels without too much trouble. Each one of these channels will have a bit of energy in it. When we're done with it, it'll measure a certain amount. Now, I've gone through this in other videos, so I'll spare all of you this information right now, but I have my high voltage on, and I have all my little gain settings. Basically, it's how the computer wants to scale this information. I'm going to do one thing and make sure that I have this set so that you can see it easily. 3 pixels. Okay, that's good. Now, first off, let's turn on the unit, accumulate data, high voltage is on, and let's see what that cesium-137 looks like. And as you can see, there it goes. It's building up, and the unit is now counts per individual channel. And if you look, we're currently in channel 396, and it's only got 20 counts. It only has 20 counts. But if I were to go over here and click on somewhere around channel 600, let's say it was 684, I guess. Look at that. Getting a couple counts a second. Another channel that's really important is this guy right here, right around 32. Now look how many that's getting. So anyway, I know, because I have, papers that explain this to me, and all scientists, I guess, have this information. I know that the two energies I'm looking for are 32 kiloelectron volts, which come from X-rays, from the decay of cesium-137 and barium-137. And also, I have gamma rays that are coming from, again, the exact same decay. And these gamma rays are at 661.66. We will round that off to 662. My machine's not accurate enough to make up that little tiny bit of difference anyway. By the way, that's this peak here. That's the 662 kiloelectron volts. Kiloelectron volt, by the way, is 1,000 electron volts. The 32 kiloelectron volts is right here. So the question is, what is this, this, and this? Well, this guy right here is a peak around 70 to 80 kiloelectron volts. Should be around 75. And this guy right here is coming from my lead shielding. Energy is hitting the lead, and I'm getting this back as a result. This is pretty much in all of my spectrums. I'm going to try to get rid of that with a little bit of tin and copper together as shielding. This right here is a backscatter peak, and this is a Compton edge. There are two little interesting facets of the detector itself and the way photons interact with matter, which are kind of beyond what I'm going to go through today, which is how to analyze this sample. So to do this simply, if we wanted to, we can stop this, and we could, technically speaking, go to energy calibration and click the auto calibrate button. If we did this, the machine would automatically calibrate it for us, but we're not going to do that today. We're going to manually calibrate. Now here's how we do. We come here and look over at this peak right here, and we're going to find probably the highest point on it, which looks to be about channel 31, channel 32, somewhere in there. We'll pick 32. It's coming up 31, but I personally know that if I run this thing for a while, channel 32 is the one that's going to come up as being the correct one. For this guy right here, it looks like it's probably channel 683. Now what we can do is we can select a region that's approximately this area and look and see what it thinks. It says the centroid is 681, and we chose 683. So that's pretty close. 681's right here, and that's what it thinks the center is, even though it's not necessarily the highest point. Just for giggles, let's try that over here and see what it thinks. 32. So that was pretty close. So we'll go with 32. Channel 32 is equal to 32 kiloelectron volts, and we're going to pick that channel 681 is equal to 662. And then this is just like, you remember in school you had y2 minus y1 over x2 minus x1, and you had the slope of a
of a equation. It's kind of like the same sort of thing. It isn't really as complicated as it sounds. We'll do a 2-point calibration. And the machine wants to know what kind of units we're using: feet, pounds, inches. In this case, we're going to use thousands of electron volts. And we're going to tell the machine that channel 32, that's right here, happens to be equal to 32 kiloelectron volts. I chose these settings for that reason. But then we're going to tell it that this channel over here, now what was that channel? 681? We're going to tell it that channel 681 is equal to 662 kiloelectron volts. And now all the bottom here changes to kiloelectron volts. And we now know that these things are around, what, 480, 440, something like that. And over here we have 280 maybe? 201? I don't know, I can't remember off the top of my head. Yeah, there we go, 200 and something. And then this should be around 70 to 80, somewhere in there. Yeah, there we go, 70 to 80. That's right. Okay, so this is about accurate. Let's clear this and let me remove my sources.
Alright, well, now that we're calibrated, we'll take the sample, place it inside the chamber in between the plastic which blocks betas, put the lead back on top, and see what we get.
Alrighty, so now we have the sample in place. We'll set our time, and let's see, what do we want to set it to? Start a calculator. Well, we know that there are 3,600 seconds in an hour, right? And we will multiply that by 6 hours. 21,600 seconds. That's how many seconds are in 6 hours. 21,600. Set. That's how long we're going to run this. By the way, live time versus real time. There are periods of time when the detector can't detect because it is down. It is waiting for the next time to be able to actually detect. This has to do with a lot of math and how often the detector is hit by gamma rays. But basically, put live time is a count of how long the machine, how long the machine has been running when it's been able to detect something, versus real time, which is just how long the machine's been running. We always run for 6 hours of live time. I've already run a 6-hour analysis with nothing in the room, no sources, no samples, no nothing. That is my background. That is everything that shows up on the detector without anything being in it. I will subtract that from the 6-hour run of the samples. Let's start it and see what we get. Now, we can come back to this in 6 hours, see what we get, and do an analysis. Alrighty, folks. Now, as you can see here, we have 600 seconds, the first 600 seconds of a 21,600 second count. That's basically like 6 hours. The first 600 seconds have been compressed into only 1 minute, so it's 1/10 the amount of time. So bear with me here. This is only 60 seconds worth of data. As you can see, all the channels are filling with counts right this moment. This is going, of course, 10 times faster than it normally does. The reality is you'd sit back and snooze while watching these slowly accumulate over a period of time. But it's kind of fun to watch them sped up. Anyway, as soon as this gets done, and we're already mostly towards the end, I'm going to let this finish for another 6 hours, which I won't bother you with because due to the power of video, I can just stop and come back 6 hours later and finish it. So then you get to see the editing and how I figure out what things are, etc. And looks like we're done. Alright, so here we are, ultra compressed. The time scale is super sped up, like 4 or 5 times faster or something. I'm taking the sample, I'm putting it in the background, removing the background, and now I'm going to go through and find things that look like peaks. Start finding them. Quickly figure out what the predominant things are. Keep recalibrating over and over and over until I figure out what it is. Then I'll use large booklets of gamma rays that I have at my disposal. Of course, you don't see those because they're not in the video. I'm sitting here thumbing through all this stuff. I have a TI-83 calculator beside me, and I'm doing math to make sure that ratios and things are correct as I go along. And it looks like I've already discovered this to be thorium predominantly. I'm recalibrating for thorium, in fact, now that I have a known point to calibrate off of. As you can see, calibration takes quite a lot of time to get it exact or close enough. I often also check against a list of known gamma energies that well, here it is, that I use for finding things, the most predominant ones. Look at that, I found another peak. Double check all of the ones around it, make sure it's real. Yep, I found the 511 keV annihilation peak. And, oh, found another one. That big light blue one you see is from the X-rays from my shielding. See, there it is in big. Oh, look, there's a little tiny one right there. I've already pretty much ruled out cesium-137 in this sample. It was kind of immediately apparent it wasn't there. And I'm testing more regions. Who needs curve fitting software? I say do it the old-fashioned way. Once you've done it the old-fashioned way, you can do it the more hardcore way after that. I take my finished spectrum and I will stick it in MS Paint. Why MS Paint? Because I don't want to spend the money for Adobe products. And I can't spell worth anything, so I always write stuff down and use spell check. Or I use Google for spell check. Alrighty. There we go. Took me long enough, didn't it? Alright, Portland, Oregon sample. Just make sure everything looks good. I'd like to point out, though, that I'm actually pretty proficient with Microsoft Paint, which is kind of a juvenile application, but by God, I've been using it since the mid-90s. You would hope I'd be good at it by now. Now, here are all the little gamma energies that I have found. I'm writing each one of them down. I'm saying such and such isotope at such and such energy. How do I know these are accurate? Because everything makes sense. If I find one and then I look to see if I find its daughter isotopes, and I look to see what ratios exist and what should be there or what shouldn't. Lots of math goes on the back end of this. And here I'm spell checking something because I can't spell. Annihilation. There we go. 511 keV annihilation peak. Looks like I'm getting close to done. Double check a few things. Now it's time to start moving this crap all over the place. Look at that. Look at that. It looks really fast too when you speed it up. The biggest problem I have, of course, is getting everything to fit up. I guess if I had something nice like Illustrator or InDesign or something nice like that, I could probably do it. But I don't have any graphic design skills, so that's not going to happen. Although I like to say this is better looking than what you get back from most laboratories. What they send you usually looks like it came out of MS Paint. Or sorry, MS Paint, that's me. Microsoft Notepad is what their stuff looks like. At least mine has color. Now, how to fit these in here? They don't really fit. Maybe I could just... There we go. But I've got to make them fit a little better. Yeah, that could have been made to look nicer, but there's not much I can do. Oh, there we go. And now let's add some touch to it. That's the sample's background, and the background to it right there. The yellow's the background, the blue's the sample. And I have them in comparison. So I'm going to grab a hold of them, and I'm going to guess about maybe 40% the right size. Nope. Try 50%. There we go. Now let's put in what they are. Alrighty. Background versus sample. Straight up 100% 1-to-1 ratio of activity. There. Now, where will this go? How about right there? Yeah, that looks good. Not really, but good enough. Now, I'm worried about the cesium-137. Let me do a double check. Clear everything out. grab exactly the ranges for cesium-137, and notice both the ROIs are negative numbers. It sort of kills that. Alright, well, there's probably no cesium-137 there, nothing I can detect anyway. Not with any credibility. And that's it. We're done.